blinded by the street lights. It's like I'm hiding in plain sight, so distant on the outside. I'm a wanderer covered in disguise. I'm blinded by the street lights. It's like I'm hiding in plain sight, so distant on the outside. I'm a wanderer covered in disguise. I'm blinded.
All right. Welcome back to the stream. I'm Agent Ultra, and on this stream we do recreational programming. Often in functional programming languages, sometimes in C, and sometimes in other languages like even Lua. Which I'm going to be working on a little project that I've been working on for a little while now, trying to figure out how to and learn how to build a MUD server in Haskell. So MUD server is a multi-user dungeon. It's the kind of precursor to massively multiplayer online games that we know and love today. But people used to play them in text. That's how it used to go. They were still real time. Multiple people connected at the same time playing the game. And so we're building that in Haskell just for learning or fun. I'm not intending to make any like kind of serious engine with this, but like, you know, treat it as a learning project. So we've been learning about multi-core and concurrent programming with Haskell in order to handle like multiple people connected at the same time and doing things. We've been learning how to embed Lua scripting into Haskell applications so that game developers who use this engine can write their code in Lua, and just so that I can experiment with like, you know, embedding other languages in Haskell. What else? And right now, for the past little while, I've been working on trying to figure out how to handle our live data and systems. So we're thinking about doing an entity component system. So I'm just bashing together some code, trying to figure out a way to structure an entity component system in Haskell, and then maybe we can integrate it into the engine and start using it for being able to implement commands in the game, like move and like moving mobs around, attacking if we want to make a more violent sort of situation happen in our game, that sort of thing. Right, but the idea is that you define all the things, all the game objects in your world with components. You identify each object by an entity or an entity ID, and you have systems that you eventually write which update all the entities' components based on like the system. So like a physics system, a battle system, and that sort of thing. Right? Okay. So it's been quite a little while since I worked on this, so I have to like reboot it into the brain here. But the general gist of ECS is mainly like components and systems. You know, the entities are just like IDs that identify these things. And as I recall, this code doesn't actually, I don't think it actually compiles, for one, in this like kind of prototype module. But we want to have our elements of our component, the fields of it, as a vector, right? The idea, that kind of one of the main driving things behind entity component systems is like more like sort of like a performance thing, which we're not super concerned with, but it's interesting to learn about nonetheless. Some people just like the API of like thinking in terms of components and systems. So we don't necessarily need the most performant implementation, but nevertheless, the idea is somewhat based around performance. So where there's one, there's many. And so the idea is not to try to treat, like have arrays of big fat objects, but have an object that has many arrays for each element, and then we index into them. So For example, this position idea, right? We have a component that is a position component. It has an X and a Y field, but instead of having a big vector of position records, which would take up a lot of space and a lot of memory, and only allow us to operate, like, as we're traversing that structure, that data, right? We have to pull in a bunch of other data into memory at a time. Very inefficient. So if we could pack things together closer that are related to one another much faster, fills cache lines, that sort of stuff. Right? Now, Haskell's not exactly the language for very precise control over memory layout. All right, it is a garbage collected language, but there are strategies we can take when we do need to have a little bit more control, and where we need a little bit more performance. So we're using mutable vectors. All right. Mutable vectors allow you to mutate the data in place, which we're probably going to be doing quite a lot with systems. And we want to split out each of those record fields into a mutable vector of data keyed by the entity ID for that entity that uses that component. And I think I ran into a little bit of a bump in the road, so to speak. I kind of came up with this idea here because our actual component design in the engine is a map of text to these like internal types, D type, right? The supported types. So the developer, the game developer, is writing these definitions for their components in Lua, right? So that we can keep the engine for a lot of reasons. One, just because why not? Two, we can keep the engine running and like we can reinterpret script, that sort of thing, these things, without having to recompile the whole code base and then run it again. All right, so we're assuming the game developer isn't interested in writing game like engine code. All right, so they don't want to be having like a big compile rerun loop. They want a quick, fast, lightweight interpreter loop, sort of thing. And yeah, so we end up building up, when we parse these components out, a big map of text to values. All right. Same thing. They kind of mirror the definition type and the value type. Same things. One thing I think we're going to run into, or I've already ran into, is the string thing with text. Keeping text data, textual data in components. How do? But numbers pack pretty well, so there's that. Yeah, and then we're exploring maybe doing some template Haskell or some way of generating the in-memory store for the component data so we can write our systems over it. Right. So this instantiate, we have a definition, we have some component values, and then we either get a component or some an error text. I mean, we could maybe just roll with that too and not really worry too much about the stuff I was talking about here. It's been fun, but yeah. So we came up with this idea here. Why did we come up with this idea? We came up with this idea because I think we were trying to split out. Yeah, we wanted to have vectors of different types in our components. Now this is a very specific component to the positioned type here. And so if we wanted to add a position, okay, this is what the code's saying, that we got to take a position component, which stores the data, and we run it in an ST monad, returning a position component result. So either we were able to add it or we couldn't. Right, success, fail. And this would be all fine and dandy if the game developer was writing a Haskell code, right? But we're parsing out the definition, the component definition, first. Right? So we don't know that it's a position component necessarily, unless we make them name them, the definitions. Well, it has a text type, so that's something. So why don't we... Why can't we just use a component like this? Sometimes taking time away from a project and stepping back into it is a great way to kind of get... It's a slow way, but it's a great way to get a different kind of perspective. Maybe we're getting a little bit too buried in ECS land. Oh, well, this would be one component. And then to have many, right, we'd have to have like a big ol' vector of them, I guess. Alright. And then, if you're to write a system, something like, I don't know, position. Alright, what are you going to do with update position? You're going to take those position components that you're interested in. Alright, you're going to do something with those. Maybe a physics component. Like or a velocity component or something like that. So you might get some component. And you're essentially going to mutate those components. So maybe even in an STS sort of situation. Something like that. Yeah. Okay. Now we have to have some way of registering the system so that it gets the components it wants, but I think that'll be orthogonal. Here, I just want to kind of sketch out stuff. So, let's see. Well, every tick that we run through this M vector of components, I got to mutate it. Each system is going to say like what, when it registers, what components it wants in this list. So we're going to have to, for every system, run through this vector of all components, right? And try to filter out the ones we want. This could be quite large. That would be a very expensive operation to keep doing. All right, so we might want to break out component into like an in-memory, like some kind of mapping. Maybe it would be a map from component type. And then to a vector of the component data. Something like this. Right, now we can say, well, give me the vector for this component type and this component type when we register the system. Right, and now it will only have to iterate through those two vectors together, which is kind of what we want, right? Depending on how we structure that, maybe it could even like generate the code to even give us the components as a tuple or something, or in some kind of structure. So if we register for 2, or we register for 3 components, that sort of thing. This might be a good enough conceptual sort of model of that. All right, and then update position could then break apart those components recursively or whatever. Right. We probably want to actually, have the registration be able to do data like this, so that if I register for, the position and the velocity components, then I iterate over them in pairs, or they could be grouped together by the entity ID. I think we could be able to do something like that. Yeah, my editor. There we go. It'd be something more like that, and then you'd have your position and velocity component, your component data there. You use the SD stuff to modify those in component data, and pacha. All right, and then so one tick of the server runs through all of the registered systems, applies their updates to basically the effect is of running each system mutates the state of the component data. We run through one cycle of them. That does mean that we're going to have like some dependency things. So depending on where you register things and in what order, some things will run before others and mutate the state before you get to see them. That sort of thing. But I think that's probably pretty expected. Hopefully. I think that's what I'm going to expect. Well, that might be fine for this engine. Okay, so what next? How do we go from here to there? Well, let's build up this component data map thing. Doohickey. Let's build it up in component. It's probably just a fine module. And let's say, let's call it a new type. So this approach is basically throwing out all the stuff I've been talking about the last few streams with breaking things up into vectors and breaking out the fields. But maybe the progress is better than perfection. And maybe what we learned is that this is fine too. But if we come up with good abstractions, we should be able to try that out underneath as well. So let's see. Okay, component data is going to be a map. We should probably maybe do mutable maps. Hash tables. Mutable hash tables in the ST monad, as well as type class or abstracted common operations, and a set of wrappers to use the hash tables in the IO monad. Okay. Good old cuckoo hashing. Nice. Good old basic linear probing hash tables. And a linear hash table. Yeah, let's try this. Although, do we need... we could start with a pure version. And then go down to a mutable one if we want. Just to get the API down. Let's just go this route. Hash tables. Let's open up that COBOL file. Put it in here. Hashable. What are we at? Like 142, roughly 47, maybe. Yep. Okay, so we'll do data.hashtable.st.basic to start. I'll bring in hash table into a type. Yeah, we'll import the rest qualified. There's H table. There we go. Okay, so then we'll make the component data such an H table, hash table. That needs SK and V. Alright, now our keys and values are known. So maybe we can get rid of K and V here, because we'll do component type. And V will be our vector type. Yeah, actually. So we get data.vector as well. We want M vector, I think. And M vectors of value. Sorry, that should be qualified, this one. There we go. Okay. So now we have a structure, hash table to store our component data. And we're going to do it the silly kind of way. Maybe not silly, but we're going to do it in a way, right? Where we're going to just store the vector of this component data, right? Instead of breaking things out into individual vectors of values like the structive arrays kind of approach. We're just going to go like a straight on vector of components. So it's going to be like a straight on vector of map values. Wild, I know. It's going to be tons of data. So much data. We're just going to throw all the data around. For all this extra structure. But hopefully it'll be fairly straightforward to implement. Alright. Okay. So now that we have component data, let's see. We need to be able to add components to it. Alright, we need to be able to initialize one. Create a new component data. And, yeah. So when we create component data, I think we want to specify how many components we're going to have. Right, at least that way we know we're going to have, well, how much we're going to have. And then we can kind of like set a memory bound a little bit. Control how much memory we're going to use. So maybe we shouldn't make the component data like unbounded. Alright, so like, and it'd be by entity. So, like say, let's have a server with 30,000 entities. Alright, so then we just have to create a component data with this hash table for each of our component types, and each of these m vectors can be instantiated to hold values. Actually, not components. This should be component. M vectors, not values. M vectors are components. Look at the definition. That's silly, right? That's just what I was talking about. The not so brilliant way to do it. Right. So it's going to use like a bunch of data because we're going to have a map in here for the component data. That's going to be inside of a mutable vector of such maps, and then that's going to be inside of a hash table, and all this sort of business. Right, and so if we're iterating over several components at once, right, we're going to be pulling these bits of data out probably right off the heap. Right. That's kind of why the ECS approach is a little bit different. Right, we can, with unboxed mutable vectors, we could pin these out into a fixed region so that they can be read more efficiently into cache lines. That's why we wanted to do it this way. Right, so that if we have systems that run on two different component types, we can pull in that component data when we run that system over all the entities pretty quickly. Right, and they have because they have all the data close together. But we're going to try this way out. Okie dokie. So let's create our initialization function. We can call it make component data. We'll take an integer of size, and we can do it in ST, we can do it in IO, that would be fine. All right, we need ST in scope. So control that monad. Bow. Okay, let's look at hash tables. In fact, we might even want to initialize, yeah, new sized here. Since we parse all of the component definitions at startup, we can just create a sized hash table here. We know the size of it because it'll be the size of... Well, it has as many keys as there are defined component types. And then this number of entities will determine the size of those vectors. There's maybe a way. IO wrappers, yeah. So, IO. Yeah, we can do the IO hash table and create our hash tables with these. Or with ST, I think is probably also okay. Not really sure which one we're going to do yet. Let's see. Num components. New sized. Num components. Okay, and now for each of those elements, we want to initialize the vector to a particular size as well. Oh, so actually, we might as well give it our make component data the list of definition. Means we have to compute the size of it, but hopefully it's not too huge that this won't be such a big deal. All right. We get a size table based on the length of the component definitions. Now we can iterate through the component definitions and update the insert into the table our sized vectors. That one comes from control.monad. That returns unit. What if we got here? We got foldm. It takes a hash table, some value A, and a function that takes that a key value in our hash table, I'm assuming. It's the KV here. And returns an ST action, returns an A. Okay, so folding over this hash table. Not quite. I think maybe we want traverse here. Or final expression in our do block that returns component data. Okay. Yeah. So now we can mutate that thing, yeah? With our ST actions. So we're going to not add that. We're going to insert which takes the hash table that we have. That's component data. The key, I believe. Yeah, and a value. So the key will be here, the definition name, definition type. And then, lastly, the value, which will be our vector. Okay, so then we need to look up our vector. Could we create this as a sized one too? That would be super sweet. Oh no, come on, tell me. Okay, there isn't. I mean, it kind of makes sense, because if we have to create a sized one, you have to give a default value for it, right? Just makes sense. And we could sort of maybe do that for component data. Right, the idea being that if you are in the vector and the entity is, your entity ID is going to be an index into there. We have, say, 10,000 entities in our map, but maybe, I don't know, entity 322 isn't used right now. So we have the data for it present anyway, but it's just not active, right? Here's your spot for entity 3. Yeah, makes sense, hopefully. And so we just need a way to say, like, entity 3 is actually live in the system or not. And then we have a default value. They're all not in use. And so when you're defining an entity, you're going to get, well, in this system, we're going to get data for all of them, no matter what. So you're going to get a component for all the defined components. And we're just going to have one or two of them active depending on the entity type that like based on the entity that's associated. Like the components associated with a particular entity. So like your mobs might have like a position component. And you might have defined, I don't know, a bunch of others, like maybe a teleportation component, but like this mob doesn't have a teleportation component. This particular entity doesn't. And so you'll still have an entry in the teleportation components vector, but you won't have you won't have any active actual using data there. You know what I mean? Maybe the better way to structure this would be with even more hash tables. Just add another hash table on it. That way we can use the entity IDs as keys into the hash tables, and then there's only live components for each entity. They don't have all the components, they just have the ones that's associated with them. Well, that might be better. Let us think about that. Take out that. Go here. Go even deeper. And then we will have entity ID to component. Even wilder. Simulation. Oops. There we go. And then empty, 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 empty. just new. Okay, so our return type here is not quite what we're expecting here. What are we getting? We're getting hash table s text, hash table sk0v0. We expected a component data. That's right. We have to wrap it in our new type wrapper. And here, component data. Oh, definition. We need the. We wanted that to be component type. The definition, it's text. Component type. It's just a new type wrapper, so that should be straightforward to fix. We can just go in there. Here. And then, what do we get? Because it changed the value of component values. Yeah. Or the type of component. And we should get rid of that. And now we have no instance of hashable for component type, our new type there. We should, because it's just text. So we should be able to do, I don't think it's stock driving. And then we need to bring in hashable. Where's that come from? Data.hashable? Super. Right. Yeah. Okay, so we initialize there from our definitions. We make some component store for that. Return the hash table component data. Okay. That's fine. Yeah, I don't know how much of a fan I am of this code yet, but it is what it is. Let's see, what else do we need to make this start happening? Right, we got to initialize, call this initialization function in our server somewhere. Just set this up and take our reference to our component data. Probably probably in the low-level server stuff. Okay, I'm gonna get. I'll leave that file for now because I might revisit it at some point. Okay, let's just review our commits here. What we got so far. Move some things around, some imports added hashables, component type. Just some white space changes there. That's not quite right. It's better. So we have the new type component data, which is going to be like our in-memory table for all our component data, and an initializer function to build one. Okay, that's it. Pretty simple, straightforward, little tiny commit. Work in progress. Component data. In-memory structure for storing component data. Live component data. Obviously, eventually, when we're running like a MUD server, we actually want to have a system that will serialize occasionally the in-memory data to store, to a more permanent store, so that we can survive server crashes and things like that. Or be able to save the state of the server. Checkpoint it, that sort of thing. But this will be good enough for now to get us going. Okay, so the next point is to probably add this to the server state, the component data. So initialize it, add it to the server state. So we might actually need an IO wrapper because this is going to be in the IO layer. A little further down in Bakamud. Maybe here. So this is the big old structure that contains references to everything used in the server. In fact, we already have server state entity components. It's a sysmap. Ah. Server state entities. Okay. It has been a while since I worked on this. Okay. So we have server state entity components here. This is a concurrent map. And like a software transaction, an STM map, basically, S map. And it goes from entity ID to a set of component type. Okay. So this is one way I was probably thinking of mapping entities to components was via their types in this S map here. To their component types, and then what? That would be an index now into this thing we just wrote. Right. Interesting. Okay, so that would be the keys into there. So we still have server state component data. Yeah, what are we going to put this in? Component data wants an S on it, which means we're going to have an S on this, which is going to be super rare. Hash table. Do you have a way for me to not deal with the S? Probably with your IO wrapped ones, I imagine. Okay. Maybe. Or we could just go ahead. I don't know if this is going to be my favorite thing. Sorry, not there. Here. So that's going to mess up a bunch of stuff. Yeah, and then the server monad is going to have to change. That's gonna change. Just there. And then these are going to need to change. Like, it's just going to spill out everywhere. Not so bad so far. Not liking it. Let's see, 126. So far it's just type signatures we are updating. Couldn't affect anything else, really. Almost phantom the S parameter here. That's just used for ST. Having to thread it around everywhere just because we have an ST drive data structure for mutation purposes. When we're getting to the server state level though, like we have a TVAR around it anyway. Yeah, still. 236. Wait, what? We missed spot 146. Okay. Simulation. And server client. Okay, so yeah, annoying, but not the worst. We just have to add a type variable all the way around everywhere. And let's look at the code. Touched a lot of places. Just mostly type definition changes. But now we have mutable component data there. Alright, so when we run our systems code, it can do all the mutations in place in one operation, in one transaction on that tvar variable, so that'll be okay. Yeah, it's not the worst. It's just working with ST. You know, just life. It's just how it goes. Sometimes you just gotta pay the price, you know? So let's stage that. Work in progress. Add component data hash table. To server state. Okay, and then I think we should update state so that we initialize that field. Okay, and put that there. State component data. Yeah. Okay. Now, we gotta actually call our little initialization thing and put it in a tvar. So we know we need to call new tvar IO on something. That something has to be component data S. We can get a component data S from our new function. Make component data. Oh, excuse me. Okay, well, that's an ST. We are in IO, and I think ST has function for us. To run in IO. ST2IO. Right, so in order to initialize that, we need the list of definitions that we've parsed. For now, we can just make that the empty list, just to get this compiling. And then what do we got? 103. Yep, sorry. I forgot to run ST2IO. We might go on a second line. That's where our change is going to bite us in the behind here. Okay, so this is because we haven't said anything about this S here. And this line, when we use ST2IO, right, fixes that S to real world. Maybe actually we don't need to run that. Maybe we just need to run the ST computation there. Maybe that's my bad. Okay, and now we have the other problem where we run the ST computation. The component data is some S, not the S. The S of this component data, the type of this component data isn't known. Or it's inferred to be something different than the S returned from the function. Good times, good times. But that's not the way to do that necessarily. Maybe the last change wasn't quite what we wanted. Can we component. Do we need the S to be part of the type here? It has to be because it's on the right-hand side of the thing. And if we fix it as... Yeah. What else can we do? It's because the S isn't showing up here, but our type is returning some S. So Haskell's getting annoyed with us. Right, because it can't match. Just the A there. When we're introducing a new type variable, I think the type of component data. So how the heck are we supposed to use or keep references to mutable hash tables if we have to have this S floating around? Maybe what we should do is forget about the mutable hash table, go with concurrent hash tables, the STM hash tables, and that's it. Maybe that should be the way to go. And then I can get rid of all this annoying parameter floating around, bothering us. Because what ST lets us do is like run all these mutations within the ST, but and that's all fine and dandy. The thing we return outside of it shouldn't have that S in it as well, right? It's kind of why it's not. Yeah. The GHC is trying to tell us things here, basically. We're going down a road we don't want to go down here. So I guess we can't really hold reference to mutable things outside of ST. We can put things into an ST context and compute it, and they're going to mutate things inside the ST. But whatever ST returns as a value, right, we can't return it. So we can just mutate it. So maybe we don't return back a component data. Maybe that's what it is. And how do we return darker? Alright, because I want to store the hash table in the server state. A reference to it. So that when we go to run the systems, they get their lock on the component data, run, mutate, that's a whole mutation, and then release the lock with the, and then the tvar will have the new value of the component data state. For some reason, I am not able to hold on to a reference to some data structure to be used inside an ST computation. So, like, do I have maybe freeze and unfreeze operations or something with these mutable hash tables? Maybe I'm not holding it right. Let's see. Hash table class. So they recommend you create a concrete type alias in your code and use this package. Table KV. So no S's here, right? Now ST Kaku SC class SH C.hash table SKV. So this has the S on it. Then we can run. See, but this one returns an S back and returns that HT, that hash table. Maybe I do need to use the IO wrappers. That's kind of where I'm using it, right? Okay. Let's figure that out then. Okay, so we have basic hash table, an alias basic hash table KV. There's IO hash table for b dot hash table KV. This module provides ST2 IO wrappers around the hash table functions. Return ST to make it convenient to use them in IO. It is intended to be port qualified. Okay. So, data hash table.io has H table. Basic hash table. And then we change this to be just hash table, and make component data the IO action, returning hash table or component data. Get rid of the S. Hopefully that all is fine. We have new sized, just like that, but now it's an IO action, an IO hash table, which is our alias here. So I think, okay. So then what do? We do component data. Turn that back into an IO action. This type can be updated here. We don't need the S here anymore, which means we don't need the S here. So we're going to undo a bunch of changes. Okay, so I'm going to stash these changes for a sec. Revert that last commit. Oh, is there template has closure? Anyways, yeah, okay, and then we fix this code. Reload the buffer. Add that field back in. I don't know, component data is good. It's the type definition up here. Yeah, and this will be our tvar component data. Down, get rid of ST. Okay, we compile. Okay, so we have empty component data, but the map is there. Okay. Good. Now, what do we need to do? We need to actually parse those definitions as startup to populate that list. So make component data creates the actual, all the maps, hash maps for us. Then we can start populating all the component values. Checksor! What's going on, friend? Oh, I gotta tell you, Checksor. I don't know if you owe me, but like I got into Proverbs hard. So thanks for that. I think that was you that turned me on to that. I've been meaning to I've been playing it quite a lot. And it got me thinking as I'm playing it, like, how does it work? So I was like, as I'm playing the game, I'm like thinking of code in my head and being like, what's the tool that the guy wrote that makes the numbers appear the way they do? I want to get the store page up here so we can see it. So these numbers here, it's like Minesweeper. Let me turn the sound off, right? And they're within regions, right? And each number represents like how many light squares the underlying bitmap are light colored in a 9x9 region around that number, or 3x3 region around that number. So like this 2 that I'm circling right here, right now. Here, this one here. I could make that just a little bit thicker so I can overwrite it so you can't see. This 2 over here means there's, in the underlying bitmap, there's 2 light-colored cells in this 3x3 region, including the cell that the number is sitting on. Really cool concept, right? So simple, so nice, so elegant. I was reading an interview with the developer, Mark French, and kind of describes the tool, but in general ways. So on my vacation last week, I was sitting on the dock and I was thinking about this, and I was like, how does it work? I want to know. And I was playing with, I was thinking maybe I'll play that on the stream, some of these ideas, but I was doing it on paper because I didn't bring a computer with me. But I was thinking maybe it is probably using, maybe he's not using it, but I was thinking I might use, if I was to do it, like either a min connected graph or a max connected graph, and just kind of start erasing out cells that aren't covered, you don't need anymore. Well, the way he described the algorithm, Mark French, is that he also has like a function that checks each region is solvable, and his algorithm brute forces it. Right, so it fills in all of the cells with a number, and then has a brute force algorithm that goes through and tries to erase cells, and then runs a checker to see if the puzzle is still solvable, and then randomly erase another cell and see if it's still possible. Which I thought was kind of an interesting approach. Sounds like something I would do, I don't know. But, yeah. I was also thinking like minimum connected graphs or maximum connected graphs might also be the way. But there's some metadata you get if you calculate the overlating matrices. Yeah, surprisingly. But it doesn't have to be super fast because it's not doing it in real time, right? The game Proverbs ships with just the one puzzle, so if it's a little bit slow to generate, it's probably okay. Anyways, thanks for introducing me to that game. I love it. It's amazing. So good. So maybe next week on the stream we'll play around with some of those ideas and see if we can't create our own similar puzzle building tool. Make our own mosaic puzzle games. Yeah, so we got the component data compiling at least. We do have... What else do I have? Already getting the component stuff. The parser for parsing definitions. Right, so we can write some code to read a directory or your Lua definition files and parse those definitions. And then we have a list of definitions that we can give to that, and then that would be, boom, loaded up. ready to go. Instantiated. Okay, so let's call it parse definition path. Parse definition path? I don't know if it's a great name. IO action returning a list of definition. Maybe give us a path. All right, so redirectory, I believe it is. No, list directory. Yes. Oh, that's the system.directory. I think that's, is that a base module? I can't remember. List directory. So we're going to list that directory and just read each proper, like, normal, like, just text file in there. Or Lua file in there, I guess. And then try to parse those with our parser. And what do we do? If any of those fail, just throw an exception because the server shouldn't start up with bad data. Sounds reasonable, right? Okay, do I have directory already? I do. We're almost out of time too. No. Okay, so what am I gonna do? Files. List directory of path. Yeah, and no, we don't want 4M under, we want 4M. Okay, then we want to read the file if it's a text file, if it's the file we want. So if it ends in Lua, do we have any functions for that kind of stuff? Move, rename, no, copy, no. Does file exist? Oh. Ooh. I need to find. Too many permissions. Okay, so we just need to check if it ends with I guess .lua. Is it giving us strings or text? I think they're just strings, so that sucks, but we will get through. Or Haskell file path operations. I think there's one for extensions, isn't there? Get file extension. Yeah, we're just I'm kind of tabling, I guess, the idea of I'm still working at Bakamud, but the implementation of the entity component system. Kind of tabling the idea of trying to use unboxed vectors for the component data and just using Haskell data structures, maps and stuff like that. Might reintroduce it at a later point, but I just kind of want to get the ECS going, and if we have a good abstraction, maybe we'll be able to change the underlying implementation if we want to explore that again. Try it out. So yeah, I'm just trying to get the ECS system, an ECS system going. Maybe not the best one, but it likes something going, you know? The boat must float first, yes. And then we can make it fast. Or better in other dimensions, as we feel we want to, you know? So we have a parser for parsing out the definitions of the components from Lua, which is cool. And I'm just going to take, yeah, there we go, take extension. Right, so it's a pure function. Take extension. That comes from good old system.file path. Okay, so if the extension is not equal to .lua, does it have the dot in it? Yeah. We'll just error for now. Or maybe we should just skip it. Oof. Been a while. Been a while since I've done some Haskell programming. Sheesh. Vacation. Working on the video game that's written in C for a couple of weeks there, so. Oof. I was trying to write a C not equals. Alright, anyways. Same diff. So then the IO definition block there. So then we want to read a file and parse definition, and if we get a component definition error, we can raise that as an exception. Otherwise, we get our definition, get our D. Ooh. Oh, we expected text. That's right. We can to from pack, unpack. Maybe definition? Oh, it's either, isn't it? Oh, just mirror. Okay, let's get rid of the ST imports. Okay, let's go to state. Let's initialize the server state. And then let's go component data. So we want to fill in this list here. Parse definitions. Parse definition path. And we'll just put some path there. What do we got? Main mud path. That's where we get our code from, right? Yeah. Mud main path. And then maybe we'll add the components directory, subdirectory of that. So then we're going to turn that here. Okay. And then if we run the server, it's probably gonna get mad at us because that path won't exist. Bakamud. There we go. Cannot load Lua code. Attempt to call a string value. Is that the right place where I was expecting it to fail? Or at least close. Server. Network server. Not quite. No, actually, this is different. Why was now that's That's because it's not finding the main module, the main mud code. We have that defined at opt Bakamud main.lua. Right, and this is where we're going to want the components directory. Yeah, oh, okay. I forget how I configure that. Maybe host name, maybe service name. Yeah, back on server. Right. The interpreter lock. Push the Haskell functions. Load the mud main module. From MC to load main. Get that. Yeah, we hard code that at opt/Bakamud. So there might, oh, maybe I got some leftover code in there that is not compiling or interpreting properly. Yeah, we have some like scratch system, Lua systems code that we were thinking about. I guess we could probably get rid of that. Those ones are fine. Let's see if we can get it going here. Come on, startup, fail, let's go. Let's go. Guess it's, maybe it is actually just running. Okay. Get a little tab open here. Get a client open and connect to it. Well, that doesn't work anymore. For some reason. Okay, well, yeah, there you go. I gotta run. Stream's done. Server's not crashing. So it's not really doing anything though with that yet, but we can now should be able to add our component definitions to that directory. Maybe that make that a little bit better. So we can move just skip Lua files, non-Lua files, and that'll be it. And then next time we work on this, we're gonna define some entities and give them some components. We will find a way to debug the state, see how it's going, and then start doing systems registration. That sort of thing, and then we can start writing some mobs for our game and some more interesting commands that use the ECS system to manipulate players instead of like hand-coded API calls and stuff into the Haskell. You just use the ECS system. So that'll be that. Great. Thanks for hanging out with me today. Thanks, Jessica, for stopping by. All you other lurkers. I'm Agent Ultra. I do these streams once a week on Tuesday evenings where we do recreational programming. We just program for fun and for the love and joy and for learning. And follow the link above my head, declarative.tv. There are other streamers that are looking for an audience. If you like Haskell, great. You'll be well served there. Also, Elixir, Erlang, and other kind of declarative style languages. Heck, maybe there's somebody doing Nix. I don't know. And there's also a link to a Discord server on that site as well. You can go to check that out. We've got a channel for this stream. So if there's a question you wanted to ask, or you want to just hang out with cool people and talk about your projects, good company there. Ant-Man went so small he could see the entities that consist of our universe. Yeah. Cool movie and concept. But man, the technicality on that one was, the effects on that one were a little, I don't know. I liked the movie, I still liked it, but anyway. Love Ant-Man. Good times. You can also follow me on Mastodon on types.pl at Agent Ultra. I'm also Agent Ultra on GitHub, where the code for this project lives. And it says Agent Ultra /Bakamud. Give me a follow there on the Mastodon. It says you'll be able to follow updates about this stream and other general programming nonsense. And have good times. Also agentultra.com, where you can find links to my YouTube channel where I back up the VODs for this stream. And if you're watching from there, you know what to do to please the algorithm. And give me a follow here, and you'll get notified when I do streams. So take care. Happy hacking out there. May all your monads be free, and may all your types check. And we'll see you soon.